So for doing this first factoring problem, we again start by looking to see what we can divide every term by, and it looks like everything's divisible by 3, and that I can pull 6 x's out of every single term. So I'm going to factor out 3x to the 6th. When I do that, in the first term, that leaves me with x to the power of 3, then plus 8x, and then plus 12. And then the question is, can we factor it any further past this? And remember, we're always looking at that result inside the parentheses, and we're looking to see if that factor is more. And one thing that tells me that it does, or at least might, is that it would have to be a quadratic. Is this one a quadratic?
No, it's a cube.
Yep, it's a cubic, not a quadratic. And because it is a cubic, we're done. We haven't learned how to factor a cubic in here. We're not going to. And so this is as far as we can take this one. That's totally done at this point. So again, you need to be able to check and see if that's actually an x squared in order to be able to take it any further. Now, of course, this is one of our themes of the year is factoring, and that is our logarithms, and we're going to pick up on the work that we did yesterday of evaluating these logarithms without calculators. So please evaluate each of these two values. All right, so as I'm taking a look at these, for this log base 2 of 32, we saw yesterday that I can read this as really saying 2 to the power of what would equal 32. So in other words, how many 2's do I have to multiply together by themselves to get 32? So let's start counting them up. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So notice it took us 5 2's to be able to get there. So then my answer here is 5. So that's what log base 2 of 32 equals. The whole thing just equals 5. And we can do the same thing for our other logarithm here too. Log base 5 of 1 means 5 to the power of what equals 1? Well, anything to the power of 0 equals 1. So in this case, it must also be a 0. And yes, that is a rule that you should know. Anything to the power of 0 equals 1. Make note of it if you don't already know that off the top of your head. Now, this is what we did yesterday with just evaluating them without calculators. Today, though, you will need a calculator. Today, we're going to be seeing how to actually calculate logarithm values. So instead of just being able to write them in exponential form, we're now going to be able to actually plug them into the calculator and see what they equal. All right, so the first question that you see up here that we are going to calculate is log of 30. Well, we can find that value by just plugging it into our calculator. If you're on a scientific calculator, so like one of mine that you borrowed in class, or typically if you're using your phone at home, it'd be the same type. If you're using a scientific calculator for this, you would first type in the 30, and then you would press the log button. So if you are on a scientific, that's what you're typing in. And it just gives you the answer as soon as you press log. If you're on a graphing calculator, you're actually going to type it in just as you see it, where you're going to press the log button first, and then you type in 30, and then you press equals. And if you do that correctly on either type of calculator, you should be getting an answer here of about 1.48. Make sure you can get that number before we proceed. Now, the good news is that that first one is nice and easy because generally your calculator has a button that's just a log button, where you just press it and it gives you the logarithm of that. But let's take a look at this next one here, where we have log base 5 of 20. In order to be able to calculate this, your calculator would have to have a log base 5 button. And it would also have to have a log base 15 button and a log base 16 button and a whole bunch of stuff like that. It doesn't have those. It just has a log button. And so because this is typical, that almost every calculator comes with just a button that just says log, we actually have a formula that we can use to change the base of this to work with any logarithm. And it conveniently enough is called the change of base formula. So this now needs to go into your notes, and then we're going to see how we can use this and apply it to find our actual values that we're looking at here. Now, as you take a look at this change of base formula, notice what it's doing is it's saying that if I have log base b of y, I calculate it by doing log of y divided by log of b. Notice that it's changing this to be able to use just base whatever our calculator has, just log. Now, I do expect you to remember it. Now, there's two ways that I remember this. One way is that I just remember that the base is on the bottom. It has a nice ring to it, so I remember the base always goes on the bottom. The other way that some people remember it, though, is that our base is written smaller and lower. And since the base is written lower, you notice the log base b is also written lower. Now, going back to the problem that we were just looking at over here, we're going to use that for this. We know that in order to calculate this value then, because it's not just log, it's log base 5, I'm going to have to do log over log. So, which number goes on top?
20.
Yep, the 20. And which number goes on the bottom?
5.
The 5. And so this is the actual calculation that we are going to be doing. So we're going to do log 20 divided by log 5. Now, let's again go through the calculation process. If you're on a actually no, let's start with the graphing calculator. If you're on a graphing calculator where it just displays it as you type it in, your life's going to be a little bit easier here because you can just type in log 20 and the parentheses after the 20 and then say divide by log 5 and press equals, and you'll be okay there. If you're on a scientific calculator, we have to be a little bit more diligent. Do it with me here. So on a scientific calculator, you'll first type in the 20 and then press log. The number your calculator is currently showing is what the log of 20 equals. So next thing we got to do is we got to divide. So then press the divide button. And we have to divide it by log of 5. So press 5 and then press the log button. The number currently displayed, though, is the log of 5. It hasn't done the division yet. So press equals to have it do the division. If you missed any of those steps on how to do that on either calculator, this is what they actually look like and what you'd be typing in and what order you're typing it in. If you did all of that correctly, our rounded answer is 1.86. Once you can verify that you got that answer for it, then go ahead and do 3, 4, and 5, find each of those values as well. All right, and then if you do each of those other ones correctly, these are the numbers you should be able to get for those other problems. And again, make sure that you can in fact get each of these out of your calculator in order to be able to now calculate these logarithms, which means that once we can calculate these values, we're now able to start using logarithms to find stuff we could never have found before. Just it took us a little while to kind of get used to kind of seeing that they are the same as exponentials, getting used to kind of that flow before we can really jump too far into this part. So we got to kind of take it in stages. Now, we're going to talk one last thing about our logarithms here, because there's been an assumption made along here. Like when we did number 1, what was the base of this logarithm? Because there technically is a base. You know, just like any time in math when something's not written in, there is something assumed to be there. So we're going to answer that question. So please take a moment, calculate each of these two values. All right, so when we do log of 300, we get 2.48. Then we go over and we do the log 300 divided by log of 10. And when we do that, we get about 2.48 again. The exact same number as we did in the first one. When you were doing this calculation, did anybody notice what the log of 10 was?
1.
It was 1. And so that's why this is actually giving us the same thing, because this is taking that 2.48, the log of 300, and it's dividing it by 1. But this also tells us something. Notice, both of these are log of 300. The only difference is that in this one I actually wrote the base of 10, and this one I did not write a base. But that tells us what the base is. When we do not write the base of our logarithm in, it's assumed to be 10. So whenever you see log of x, it's actually log base 10 of x. That's the assumed number. It's not a 2, it's not a 1, it's a 10. Because we do math in a base 10 operating system, in case you're curious why. So now switching out of logarithms for a little bit more practice with what we were doing earlier, like yesterday and the previous couple weeks. We're going to do another story problem, but this time I don't want you to have to worry about writing it all out. Just take a moment and read through it, and then I'm just going to walk you through this one rather than you having to do all the writing. All right, so in this case, you can see that all of these different combinations cost $20. And we want to figure out what the monetary value is for each token. Now, since I'm going to then be looking for a monetary value of each token, like for the gold, when I use the letter G to represent the variable, G here isn't the number of gold tokens. G is instead the value of each gold token. Okay, so as we go through and we talk about these variables, that's what we're going to be looking at. So with that in mind, then I can get one equation just from that, right? So 14 gold, so I have to do 14 times G. And then I have to add the 20 and add the 24 bronze. And all of that should equal a grand total price of $20. Now, of course, I got that from taking this combination. I can do the exact same thing with the other two combos. So this combination and this combination will also give us equations. And so if I take each of those and write an equation form, then this is my 3x3 system. Now that I have the 3x3 system, we're solving our system. So let's actually take a look at solving. First, think about which variable would you want to eliminate first? Yep. So looking at them, it does look like the S is going to be easiest, right? Because like I can turn this 5S into a 15 or a 20 pretty easily. That doesn't work out so well with the G's or the B's. So knowing that I'm going to be focusing there, I'm going to go ahead and just pick 2. Certainly I need to use the third because the 5 is the one that's easy to make into something else. I'm going to do the first and the third at the moment. If I'm going to combine the first and third, what do I need to multiply the third equation by?
3.
Well, I'm going to want this to become a 20, specifically a negative 20. So yes, negative 4. Now, once I multiply it through by negative 4, then it's just a matter of adding the two equations. And yes, that S value should eliminate when we do so. And so notice what that got us here. This is our first equation where I eliminated S. Remember, our goal is to eliminate it twice. So having done that, I now need to work on eliminating S again. And remember, I chose to eliminate S because the third one works really nicely. So this time I'm combining the third and the second. What am I going to have to multiply the third equation by in this case? We got to multiply it by negative 3. And so then, that then gives me the S's that will eliminate. Then I can go ahead and start adding them up together. And when we add them, I again get another equation that does not have S in it. So I've now eliminated it twice. I got 2 equations with 2 variables. Now that I have my 2 by 2, we're going to finish solving it from here. Now, again, take a moment, look over this one, decide which variable are you going to try to eliminate in this case. All right, so as I look at it, I mean, either one can be done, but I think the B's look like they're both smaller numbers, so I'm guessing that's probably going to be the easier one to work with. So I'm going to try to eliminate the B's. Now, one way you could do it is you could go ahead and just try to multiply 28 by 20, and we could do it this way, like a negative 20 and a positive 28, and that would work. But something I want you to notice here is that both of those are even. And that already tells me that since there's a common factor between them, there probably is a smaller number that I can make both of these go into. So I kind of want to go through that process about thinking about what that smaller number would be. So then, for finding that, well, let's start with the bigger number here, the 28. What can I make the 28 so that we can actually get the 20 to go into it? 28 twice, would 20 go into that? If I did 28 times 2, do you think 20 would go into that? It doesn't seem like it, because, 8 times 2 is going to give me 16. So It doesn't look like something that's going to end in a 0 to me. What do you think I should try multiplying that 28 by? 5 would make sense, yeah, because if I multiply that top one by 5, well, what's that give us? Yeah, it gives us 140. It ends in a 0, so that's at least a possibility, right? Does 20 go into 140? Yeah. What would I have to multiply the 20 by to make it into 140? 7. And of course, I need one of them positive and one of them negative, so I'm going to choose to multiply the top one by the negative 5 and the second one by the 7. And so if we do that, then we get the b's set up to be able to cancel out. So I got 140b and negative 140b. I can go ahead and add those together. And we solve it out, and you find that g is 0.5. And yes, g is a decimal, and that's okay. Remember that g represented a cost. And so this then represents like that it's 50 cents per gold ticket. All right, now that I know g, which one am I going to find next? Should I go find the s next or the b next? Well, notice what equations we were just working with. All of these had g, which we found, and b in it. So yes, we're going to find b next. And so I plug in my g value into one of them. Doesn't matter which one, but pick one of them. And we solve that out for b. So b is 0.25. Or in other words, b is a quarter. Each of the bronze tokens costs us a quarter here. And then finally, now that I found g and b, now I can find s. And to find s, I can plug it back into any one of these original equations. And again, it doesn't necessarily matter which one, just pick your favorite. Or if you need to arbitrarily pick one, you could always pick the first. So if I then solve that for s, we find that s is 35 cents. 0.35 there. All right, so we quickly went through this, yes. But from here, I now know those values. Let's follow up with what else can we do with this information? Because just finding out the monetary values, oftentimes that's not really a big deal. Not all that helpful necessarily in what we were trying to find, depending on what all you're looking for. So one last question. The same arcade offers another deal, where for $50, you can get 40 gold, 64 silver, and 27 bronze. Is that a good deal? Well, without having just done the work we did, that would be a really hard one to know, right? Without having just done all of that work. But having done that, we have some context. Because with the work we just did, we found values that we could assign to each one of those. Well, we could now figure out how much this should theoretically cost us, right? Now, is it true that the big one is always going to be the best price? Like, is the $50 one always going to be a better deal than the $20 one? Not always. You always got to check it. So, if I'm going to check it, I can actually do the 40 times the 0.5. And I can do the 64 times the 0.35 and the 27 times the 0.25 to figure out what should this cost. Like, what's its actual monetary value here? And if we work that through, we get 49.15, or in other words, $49.15. Is this $50 package a good deal? Not particularly.